Hello everyone, this is Codyssi day 17 and this is a commentary, it's not a live solve. That's because like the last days are a little bit hard and sometimes I don't have the time to record a whole video of like maybe 1 or 2 hours. And lately I've been quite busy with university, so here we are just with a commentary for spiraling stairs. So basically in part 1 we are given this input, so an input of this kind. You don't care about this line, you just care about the first line and the possible moves. Basically you have a stairs made of steps from 0 to 6 and you have to count in how many ways you can reach the last step if you can do only this kind of moves. So either move ahead of 1 step or move ahead of 3 steps. So if you want to visualize this a little bit better, you have this sort of stair. You are here and you want to know in how many ways you can reach this point if you can either jump of 3 steps or 1 step. And this is a classic dynamic programming problem where basically f of n is equal to f minus, in this case, of n minus 1 plus f of n minus 3. In the case where you can just jump of 1 or 3 steps. It's basically the Fibonacci sequence, similar to the Fibonacci sequence. And so in this case, I think I used memoization immediately, but I don't know if it's necessary, but I mean, use it, like, since it's a couple of lines, there's really no way to, like, just don't waste time. So if the case is less than 0, then we return 0. If it's exactly the case 0, so if we are at the first step, then we return 1. Otherwise, we go in every move, we iterate on the moves and just increment our final result, and we return it. So very, very simple dynamic programming solution. So then part 2 is a little bit more interesting. And basically, you also have to consider the other lines in the input. So, for example, this one or these ones. These ones. So basically, as you can see here, the steps have an entry point and an exit point. And basically, what this means is that let's make this little example. What this means is that you have this sort of representation where we have like start here and end here. So this is why the first stair is from start to end. As you can see, the second stair is from S1 to S1. This means that we go in step number 2 of S1. And so this is the entry point. So basically, we can build something like this. And the exit point is 3. So this is the graph that this sort of input creates. And the cool thing about this graph is that, and basically our goal is the same. So we always have to know in how many possible ways we can reach the end. And in this case, let's say that we want to do 1 step, we can either go there or we can go here. If we do 3 steps instead, we can do 1, 2, and 3, or we could also do 1, 2, and 3, and such. So the cool thing is that this graph here is a DAG. So it's it's an acyclic graph, and this will sort of be useful later. So basically what I did is like I started to plot these things, and I realized that they were all DAGs like this, so with no cycles. And I tell you this because my first solution was to just like, without knowing that this was a cyclic, I just tried to brute force, like to do a backtracking search and literally try every possible path to the end. So that would take basically exponential time. And it wasn't doable. Like the input was just too big and the graph was too big. But since this is a DAG, so we have no cycles, we can still use dynamic programming to solve this problem. So basically, the only thing we have to say is that to reach any point, so it's literally the same as before. The thing is that for each point we can let's say we are here and we want to know in how many ways we can reach the end from this point here. What we can do is we can say we can reach the end. So f let's call this x. So f of x will just be in this case, let's say the possible moves are 1 and 3. So we can reach this one, we can reach this one, or we can reach this one. So we can say that f of x is equal to f of alpha plus f of beta plus f of gamma. This is more of a y. So the number of ways is just the number of its successors added up. And we can do this because we have no cycles. If we had cycles, this wouldn't be possible. Otherwise, you can visualize it the other way around. So let's say that you are in the end here. You can say that f of end is equal to, in this case, it's just these 3 nodes. Sorry, let's call end this, actually this node here. Say this is the end. So we have 1, 2, and 3. So x, y, z. So f of n is equal to f of x plus f of y plus f of z. And this is, again, a dynamic programming solution. You can build it bottom up if you are a diligent guy, or you can build it top down with memoization if you want. You can do whatever you want, but this is pretty straightforward to implement. The only thing here was to I wrote this get neighbors, which basically takes in a node the possible moves, the graph, and returns the list of possible neighbors. That's because every time when we are on a node, we want to understand what are the neighbors. So which points we can, like what nodes we can reach from that point. And you can either build like add some edges so that you represent this information, or as I did, I just called this function every time I needed it, which is a lot slower, but it was more convenient for me. And then, as you can see, at the end of the day, the DP function is very simple. It was basically the same as before. So if you reach in this case, I went, let's say, from the end to the start. So I built the reverse of this graph, but it's literally the same. So if I reach the start, then I return 1. Otherwise, I iterate on the neighbors and sum up all of the ways to reach the start from the node. Then for part 3, what we are asked is, given basically they say, okay, so we have our path. So our paths are like, I don't know, S1, 0, S1, 3, S2, 4, and S2, 6, and maybe S1, 6. Let's say this is our path, this is our first path, and let's say now to have another path, so like S1, 0 to S1, 4, and then like here S2, 4, S1, 6, for example. Now basically in the first this whole description here just says, okay, if you have these two paths here, you can define a safety metric, meaning that one path is safer than the other. So let's say that this is called X and this is called Y. Path X in this case is safer than path Y because the first non-matching node that they have is this one, the first node in this case. And in this case, S13 is, let's say, lexicographically lower than S14. Lexicographically is not a really good word, but because basically, for example, S10.4 would be after S9.4. But if we just look at the lexicographical order of things, the strings would be reversed. But you know, like in this case we have a 10, in this case we have a 9, so this one is, let's say, is safer than this one. So you just compare them like this, and in the case where the first, let's say, the name of the stair matches, then you look at the step number. So they just tell you that there's this metric to compare the safeness. And the weird thing here is that they ask you for the ith more safe path to reach the end. And this is a very huge number. So my first idea was obviously to memorize all of the possible paths, but this obviously is not possible. You cannot memorize all of them and order them and take the one with this index, because as you can see, this index is super huge. So what's the idea here? And it took me quite a while to realize how to make this work, and I also have to thank a guy on the Reddit which answered to my questions, gave me a couple of hints. But the idea here is that, let's say that you are on a node. So you are on node N. So this node N will have some neighbors. Let's call them X, Y, and Z. And so we already solved part 2, so we know what is dp of n. So dp of n, let's say it's I don't know, 75. In this case, it means that there are 75 paths to the end which end with the node n. So they have in common the last node n. So now from n, when we branch, so when we try to go, for example, to x or to y or to z, then we differentiate. So we take a node, we go in a path where the next node is different if we take this path, or this path. So the core idea is, let's say that I want the ith node. So let's say that e is like 200, okay? And we know that dp of dp of z is 40. It it means that there are 40 nodes which start with the letter Z and go on, so they have something here. So these are like Z, so they're like N, Z, and then something. These nodes here will be NY and then something. These nodes here will be NX and then something. As you can see, it's useless to go explore this branch because we will not for sure reach our ETH 200, our path with index 200. So we can just eliminate this branch and decrease our E to 160, because all of these nodes, all of these paths will be ranked from 0 to 40, and actually to 39, but let's say 1 to 40, whatever. There are some off by ones here, but it's not important. And that's because Z is the lowest one in the lexicographical order. So as you can see, we have these. Now let's say that here in the Y branch, we have that dp of Y is like 120. It still makes no sense to explore this branch since our target is 160. So we can eliminate this branch and say that this guy becomes 40. Now we will for sure need to explore this branch and go on. So maybe X will have some more neighbors. So maybe X will go to Y again, and then to alpha, and then we can go on. Basically, when we reach a point where, like when we reach the end node, then we are sure that we explored the safer path, or the path that, not really the safer path, but the path that reaches the index that we want. So the only thing here is that you have to make sure to sort of order these nodes in a lexicographical order, like in the order here that they describe. So every time that you iterate on the neighbors, you always need to give precedence, to give priority, I mean, to the node with the smaller node in lexicographical order. So the code will be something like that. So this is C. So in this case, instead of storing the nodes like S110 or S213 or stuff like that, I just memorize them as tuples. So 110, 213. This way, when I compare them with Python, it's automatic. I mean, Python will compare the first numbers and then the second numbers, so that you don't have to write a custom compare function. Then let's say the search function is pretty straightforward. So we take node is the first, at the beginning it's just the starting point. We set current equal to node, and then while current is different from the endpoint, where endpoint is the last node that you have to reach, as you can see here, you just take the neighbors, you sort them, and then if the target is greater than the number of paths that start with that node, then we eliminate that branch. So we don't explore that branch, we go ahead. Otherwise, if we find an interesting branch, then we go there. So we append the node to the path that we will return at the end and change the current node. And really, that's it. So this was very, very easy. If like the things that you, for part 3, it was easy if, first of all, like part 3 was easy if, first of all, if you wrote dp bottom up for part 2. And with bottom up, I mean, I don't mean the bottom up, let's say in the proper, like bottom up in the DP way. I mean bottom up, with bottom up I mean in this case, let's say that you are on this node and you have some neighbors and you go, let's say, forward, so the end is here. So you don't go reverse. So you don't say, okay, I'm here and I want to know in how many ways I can go back, or in how many ways I could have reached this node, but the other way around. So I am here, I want to know in how many ways I can reach the end. So I mean bottom up with bottom up I mean this. And second thing, it was easy if if you memorized nodes as tuples, so not as strings. In that case, it was just like you just have to write like these 10 lines of code. And yeah, so that's it. It gives you the answer in like a few milliseconds. Like the code is actually pretty fast. So input, and you should also actually give in this note this number here. Where is it? Here. But as you can see, it's very fast. So this was the final answer for my input. Okay, see you next time.